Hello and welcome to another eMathInstruction Common Core Algebra 1 lesson. I'm Kirk Weiler, and today we're going to be doing Unit 6, Lesson Number 8, Linear versus Exponential Functions. Two of the most important types of functions that are out there used to model things in the everyday world, and we're going to look a little bit at that today. Now, before we get on to the lesson, let me remind you, you can always click into the video's description right underneath it to get the worksheet that goes along with this lesson, along with the homework. As well, remember at the top of the worksheet is that QR code. What that's going to allow you to do is use a QR code app reader that you can get easily and for free on either of the major OS systems. And you can just scan that code and it'll take your smartphone directly to this video. These videos are optimized for the smartphone. They look the best on them, although we think they play pretty well on other things. All right, let's talk linear and exponential. Now, as we begin, linear and exponential functions always have basically two general characteristics. They're either always increasing or they're always decreasing. We're going to study other functions later on that sometimes increase and sometimes decrease, parabolas or quadratic functions being sort of the most major type. But these functions, linear and exponential, they only ever get bigger or get smaller. So let's take a look at a little demonstration of that. All right, here we've got in the blue a nice increasing linear with a constant slope. But here comes the exponential, right, in red. It's slow at first, but it picks up steam, getting faster and faster. Now we can also have decreasing curves. So a decreasing linear, simple enough, coming in the green, right? And I gave it exactly the opposite slope of the blue. And a decreasing exponential. Some nice symmetry going on in these graphs. But remember, you know, the real kind of key to linear functions is that constant slope. Exponential, but we're going to see not so much. So let's take a look at their general forms, right? Here comes our linear. In general, right, we like to model linear functions with this y equals mx plus b form. Remember, what that really means is that we're starting at this value of b, right? When x is 0, we have a y-intercept of b. And then what happens is every time x increases by 1, every time we go to the right one, we get to add m. All right, now I know a lot of times when you think about slope, like the slope is 3 divided by 2, you think of that as, oh, I go 2 to the right and 3 up. But it's very, very helpful if we think about m as being what's known as the unit change. In other words, how many miles do we get per hour? How many dollars do we pay per 1 gallon, right? So whenever we're dealing with a delta x of 1, we're really, with the slope, just talking about how much we get to add on to the y variable. Now with exponential, it's very, very similar, right? We've got this y equals a times b to the x, and I know all these formulas can kind of get crazy with the letters, but really what that means is that we start off with some value of a, an initial population, an initial amount of some type, and then for every delta x of 1, each time we go over, increase our x by 1, we multiply now by b. We don't add m, we multiply by b. So essentially, both linear and exponential start at a given point. In linear it's called b, and confusingly enough in exponential it's typically called a, but what are you going to do? And then you start with that value, and then with linear, for every time x goes up by 1, you add m. And for exponential, every time x goes up by 1, you multiply by b, by the base. All right, that's basically it for the whole lesson, believe it or not. But now we're going to do a little bit of exploration of those topics and some problems. So let's do it. All right, in exercise number 1, we've got two tables. All right, we have to be able to deal with functions that come in tables. And in this problem, one of the tables represents a linear function and one represents an exponential function, and we want to figure out which is which. So here's what I'd like you to do. Pause the video right now and look at what the y values in these tables are doing, right? What's the pattern that you see? And then think about whether that pattern indicates a linear pattern or an exponential pattern. Pause the video now. All right, let's take a look. Well, what was the pattern that we had in table 1? All right, now it's important to understand that in both of these tables, delta x, the change in x, is 1 unit, all right? So in other words, to get from one x to the next, what I would do is I'd just add 1. Remember, deltas are how much you add or subtract. Sorry, the word table there got in the way. This is the case in both tables, so I'm not going to write it out both times. And what did we see? Well, what I hope that you noticed was that each one of these y values was the previous y value multiplied by 2. All right. So what this function rule is in table form says, hey, every time that delta x goes up by 1, I'm going to multiply by 2. Okay? Let's just reserve judgment. Let's leave it like that for a minute. Now in table 2, again, the x values are actually the same. What's important is that we're adding 1 each time. But what was the pattern with the y? It looked like here what was happening is each and every time I got to add an additional 3. Right? So when x went up by 1, I got to add 3. We could even say delta y is 3, because remember, that's what's happening. Here the delta y's are constantly changing. Here delta y is 5, here delta y is 10, here delta y is 20. A little confusing. But what that should lead us to understand is that because exercise number 1, table 1, is all about multiplying by 2, this is in fact our exponential function. Exponential functions are all about getting y values by repeatedly multiplying. Here, repeatedly multiplying by 2. On the other hand, table 2 represents a linear function. And it's linear because every y value is gotten by a constant additive process. All right, so multiplying and adding, right? That is really the biggest difference between linear and exponential functions. Linear functions are based on adding, exponential are based on multiplying. The real question is, what do you add and what do you multiply? In the case of linear, if delta x is 1, you're always adding on the slope, the unit rate, right? Again, try to put it in a real life terms. Imagine that you're driving down the highway at 55 miles per 1 hour. That means every time I add an hour to the amount of time I've been driving, I add 55 miles to the amount of distance that I've driven. All right? So whenever we have a delta x of 1, it's very easy to figure out the slope. It's also very easy to figure out the exponential multiplier in this problem. Let me go back to blue. All right, so exercise 2 asks us to find the equations for both the exponential and the linear in standard form. Now, one thing that's kind of tricky for a lot of students is just kind of that pure piece of knowing what the form of an exponential looks like. The form of an exponential looks like y equals a times b to the x, right? Where a is your initial amount. It's the amount that you have when x is equal to 0. Right? The amount when x is 0. Now, luckily for us in this table, that's very easy to tell. If we look up at the table, right, we have a y value of 5 when x is 0. Now b, well, b is the multiplier for, and this is key, for a delta x of 1. Honestly, if delta x was more than 1, if delta x was 2, 5, 1/2, anything else, this would be pretty challenging. Figuring out what we multiply, we always want to bring it back to what we multiply per delta x of 1. You're going to deal a lot more with those type of manipulations in Algebra 2, and you're going to get a lot better at them. But for right now, we're going to keep delta x of 1. The beautiful thing is, again, here it's very simple. B is equal to 2. So our equation is simply 5, what we're starting with, times 2, our multiplier, raised to the x. There it is. Nice. Don't forget, you can test these. I'm not going to take the time to do it right now. It'd make the video way too long, but you can test them. In other words, take values of x here, put them into this formula, see if you get those values of y. Let's transition over to exercise B. Number 2, letter B. Right? So for a linear function, I would always suggest immediately write down y equals mx plus b. All right. Again, b, let's go there. That's our starting value. It's our y-intercept. All right. And in this table, again, very, very simple. We can just go up and it's right there. Our y-intercept is 8. Simple enough. Now, m, the slope. Typically, the slope takes a little bit of work, right? Because you have to think, oh, the slope is the change in y divided by the change in x. If you've got a couple points, maybe you have to substitute them in. We actually have a lot of points. But the point here is it's very easy. Because delta x is 1, right? When we found out that delta y was 3, what we find is that the slope just is that 3. And I really want you to try to nail that down. When you know you have a delta x of 1, then whatever your delta y is your slope. That's the point. We really want slopes to be how much does y change for a unit change, a 1 unit change in x. So what we have here now is y equals 3 times x plus 8, right? Understand what those parameters really are in the linear and exponential model because they'll make your life a lot easier. In the exponential model, a is where we start, and b is what we multiply by for a delta x of 1. In the linear model, b is where we start, and m is what we add on for a delta x of 1. Okay, I'm going to scrub out the screen here in a second, so pause it now, record down anything that you need to, and then we'll move on. Okay, here we go. Let's move on to the next exercise. Okay, in exercise number 3, we're given 2 points, 0, 12, and 1, 3. And what we're asked to do is to create a linear equation that passes through those points in standard form, and an exponential equation that passes through those 2 points in standard form. So let's do it. Let's start with the linear. All right, I'm going to write down my 2 points right here so it's easier and I don't have to really go back. Now, one thing that I noticed right away is that my delta x is 1, right? I just increased x by 1 to get to that x value. So for a linear function, y equals mx plus b, I need to know 2 things. I need to know where I start at x equals 0, b is equal to the y value, and I need to know m, right? I need to know the change in y divided by the change in x. Well, now, think about what the change in y is here, and pause the video if you need to. I need to make sure that you get this right because it's a little tricky. All right, let's take a look. The change in y here, and it's very important, is -9. All right? When x increased by 1, y went down by 9. Now, you would get that if you just sort of did your y2 minus y1 formula, right, which would be 3 minus 12, which would give us that -9. But what a lot of students will do, and this is very understandable, is they'll see that 12, they'll see that 3, and they'll say 12 minus 3, 9. And unfortunately, the problem with 9 is that it indicates that y is increasing as x goes from 0 to 1. And in fact, y decreased as x went from 0 to 1. Now, the great thing is that delta y automatically gives us the slope, right? Because the change in y divided by the change in x gives us -9. We're ready to go, aren't we? We already know what b is. B is the output, the y value when x is 0, so we have it, it's 12. So y is -9x plus 12. All right, great linear model. Time to do some exponential. I'm going to write down the points again, just so we have them right here, 0, 12. The exponential is a little bit tricky too. Here we go. Let's write down our general form. Y equals a times b to the x. Do you know either one of these easily? I want you to pause the video for a second. One of these two is very, very simple. Either the value of a or the value of b is very easy. Which one? Hopefully a, right? A is the starting value. It's the value when x is 0, and that's 12. Remember, when I talk about the value, I'm talking about the y values, the outputs to the function. Now the b. All right, this is tricky. Pause the video if you think you can figure out what it is on your own, all right? Let's go through it. Again, we face the same little hurdle that we did in linear, but in a slightly different way. You see, it'd be very easy for people to look at the 12 and look at the 3 and think, oh yeah, sure, the multiplier is 4. But the point is, you're going from 12 to 3. And if you multiply 12 by 4, you don't get 3. So a real good way to figure this out is to just literally set up an equation. Say to yourself, all right, if I took 12 and I multiplied it by b, I have to get 3. Now I'll get b by dividing both sides by 12, and that'll give me 1/4. In fact, you can always figure out what the b is by taking the second y value and dividing it by the first y value, but you have to do it in that order. You have to do it as y2 divided by y1. You can't do it in the way that makes it just easy to think about. So let's write our model. Y equals A, 12, times B, get that B in parentheses, 1/4 to the x. All right. Now, the last part of this problem actually asks us to bring in our graphing calculator, and this is the first time I'm going to do one of these in these lessons, so forgive me if it's a little bit choppy. And in fact, I'll probably have to cover up a little bit of the work that we just did in order to really put the calculator on the screen, but I want to try to keep the problem on the screen as well. So, all that being said, I'm going to open up the calculator now. Okay. Now, the first thing that we want to do is put these equations into y1 and y2. I'm using a TI-84 Plus. If you're using the TI line, this should be easy. If you're using something else, it might be a little bit more challenging, but hopefully you know your own graphing calculator. So, I'm going to go into y1. All right, I think I'll put the linear in y1. Sorry, I have to go into y equals. But I'll put in negative 9x plus 12. All right, make sure it's in there. Make sure I don't use the subtraction sign. Got to use the negative in front of that 9. Okay, let me put in y2. All right, I'm going to put in 12. Put in those parentheses. 1 divided by 4. Okay, put in the parentheses. Use that caret button, that raised to button, raised to the x. All right. Now, I gave you the window here because although it's really good to play around with windows, we have to be able to move through the lesson fast enough to not have to take that time. So we're going to use that exact window. So be careful. Hit your window button. For x min, we're going to put in negative 2. Always pay attention to the window I give you. If you don't, you may not get the graph that I want you to see. Put in 2 for x max. I'm going to leave x scale to be 1. Y min, put in negative 5. Y max, 15. Y scale is 1, that's fine. We might want the y scale to be bigger, but we'll keep it the way it is. And now let's go up and let's graph this thing. I love seeing these graphs. Takes a little while on the computer, longer than it probably will on your calculator. But look at the two. Isn't that neat? That's really kind of cool. Now, we are going to want to sketch it, so let's do that really quick. Okay, one of the cool things is that both of them go through the same y-intercept. They both go through a y-intercept of 12. Now, the linear one just comes on in. Oh, that's an interesting looking linear function. I apologize for that. You know, it just kind of comes on down with a slope of negative 9. And then the exponential, let me put that maybe in red, comes on down and intersects it like that. All right. So I'm going to clear out the text here in the moment, and we'll get rid of the calculator, and we'll move on. Okay, here we go. All right, what I'd like to do next is to actually explore a little bit about the average rate of change for an exponential function. Now, I can't emphasize this point enough. What makes a linear function is the fact that it has a constant average rate of change. All right, it has a slope that is the same everywhere. It's what makes it straight, to be quite honest. What makes lines straight lines is the fact that their rate of change, how much you add on to the y for every unit increase in x, always remains the same. All right? So that begs then the question always when we look at a nonlinear function, a function that is does not give us a line, then what does its average rate of change do? So in exercise number 4, we have a pretty simple exponential function, going back to the blue. We've got f of x equals 4 times 2 raised to the x. All right, so 4 is our initial amount, and you can see that right here. And we're doubling each time, right? So we're going from 4 to 8, right? We're going from 8 to 16, etc. So for every delta x of 1, right, we're doubling what we started with, which was the 4. So covered ground in the last couple of exercises, I know, but why not? Now, what the problem asks us to do, though, is to find the average rate of change over the various intervals. Now, remember, all average rate of change is f of b minus f of a divided by b minus a. right? And I mean, what could be more clear than that formula? I mean, there's F's, there's A's, there's B's, there's everything. Formulas can be a bit annoying. They're great because they're algorithmic, but there's all sorts of letters. Look, hopefully this doesn't make it worse, but it's the change in y divided by the change in x, right? It's how much y goes up divided by how much x goes up. So on this first interval where it says 0 to 1, right, what we can see is that the change in y, right, which you can calculate if you want as 8 minus 4, is equal to 4. Now, that also happens to be the average rate of change. This is going to make this a very quick exercise because delta x in this case is always 1, so the average rate of change in this particular problem is 4. And in letter B, the average rate of change will also just be its delta y, same for C, same for D. Because what we're really just saying is every time x increases by 1, how much is y increasing on this interval, on this interval, on this interval? So pause the video now if you wouldn't mind and finish off those average rates of change for B, C, and D. All right, let's take a look. Should be pretty easy for letter B. Let's see if I don't lean into the camera too much and knock it over. From 1 to 2, we can look at this y value and subtract this y value, so 16 minus 8. Or you can just think about what you have to add on to this y value to get to that one. Delta y is 8. That also means the slope, or the average rate of change, is also 8, because it's 8 divided by 1, or 8. Now, for the next one, we've got delta y equals 32 minus 16. So delta y is going to be 16, and that will also be our average rate of change. And finally, same song, fourth verse. In other words, kind of repetitive. So in this case, delta y is 32, and our average rate of change is also 32. All right, I'm going to just circle those in red so they really pop out of the screen for us. Here they are. And one thing that should be completely and utterly obvious is that they're not constant. In other words, if this were a linear function, what we would find is that that number would be the same each and every time. It would never change. All right, for a delta x of 1, we would get the same delta y each time. Now, I know that letter E probably states the completely obvious, but what is clearly happening to the average rate of change as x gets larger, and this is important, it's getting larger. Now that's really all I need you to get out of that, is that it's getting larger. You might even notice that it's doubling. And that's kind of cool. And that absolutely has to do with the fact that the base of the exponential is 2. But don't get it quite confused with the base being 2. All right, it's definitely a result of it though. So this is kind of cool. If this had been a linear function, that average rate of change would have remained the same the entire time, but it's not. It's an exponential function, and not only is it not remaining the same, it's getting larger, kind of in leaps and bounds. All right, I'm going to clear out the text, so pause the video now if you need to. All right, here goes the scrub. Scrubbed. All right, let's move on to the next page. So the last little exercise, we're not going to have to actually come up with any equations ourselves. We're just going to have to graph them, because one of the cool things is that an increasing exponential, and we're not going to talk about the decreasing version right now, but an increasing exponential, as we saw in the last exercise, has a slope, or an average rate of change, that is always getting larger. All right, it's almost like the y values are speeding up as they move along, okay? On the other hand, linear, no, the average rate of change is always the average rate of change. So we're going to look at a linear function and an exponential function in this particular problem strictly on our calculators, and it's really cool. So we're going to take a linear function, y equals 20 times x plus 5, and I just really want to point out that 20 is its slope, and that's a pretty big slope. You know, you're probably not used to actually graphing lines that have that kind of slope. I'm just going to kind of erase it to get rid of it now. The exponential function, y equals 5 times 2 to the x. Notice y-intercept of 5, y-intercept of 5, both have y-intercepts of 5, so they start at the same location. We're not going to be worried about any negative x values here. We're going to let them start at x equals 0 and see what happens. And what I'd like you to do is investigate what both of these graphs do in sort of different windows, if you will. So In letter A, what I'd like you to do is sketch these two graphs using the window that's indicated. Now keep in mind, I've put the 5 on this graph because I want you to realize that that's where the graphs start. But to use a window, you should definitely do 0 to 3 in the x direction and 0 to 30 in the y. On this, you should be doing 0 to 6 in the x direction and 0 to 150 in the y direction. So pause the video right now, take as much time as you need, and sketch the graphs for both A and B, okay? And you want to do both the linear and the exponential on both sets of graphs, plus label them with their equations. All right, let's go through it. Now what we're going to do is we're going to, again, bring our calculator out. Let's do that now. All right, now in order to do graph A, what I'm going to have to do is cover up B, all right? So then we'll move the calculator over and cover up the other one. So let's go in, clear out our y values from before, all right, and put in our new ones. This will take a little bit of time, but we'll put in the linear first. So it'll graph first, 20x plus 5. Okay, the linear looks good. We double check. Make sure we didn't leave out the x. Go down, let's put in the exponential. Let's do 5, parentheses, 2, parentheses. Don't forget that caret button. Otherwise, you're just doing 5 times 2 times x, and that would be linear again. So, okay, look at my exponential, make sure it looks good. All right, let's go into the window. X min, we're going to set at 0. X max, we're going to set at 3. Okay. Keep the scale the way it is. Y min, we'll go down 0. Y max, 30. Okay, take a look at our window, make sure we didn't mess anything up. It's very, very easy to make graphing mistakes if you're too quick on your window, if you accidentally just put something in the wrong spot. 9 times out of 10, that's the deal. So if you have an error, go back to that window and see if you've put it in correctly. But it looks good. So we're going to hit graph. Takes a little bit of time. But pretty easy, right? Remember the first one graphed was the linear, and the second one graphed is the exponential. So what I'm going to do now, while that's sitting there, is I'm just going to be kind of good about it, and we'll just graph our linear here. I think I'll switch up my color and graph my exponential. I didn't make the linear go quite far enough, but that's okay. All right, we'll put the equation, y equals 5 times 2 to the x. And I think we'll put the equation here back in blue. Y equals 20x plus 5. Now what's amazing is that when you look at this graph in letter A, it's like, wow, the linear, it's beating the exponential. You know what I mean? It's getting to higher y values for particular x values quicker. You can always kind of look at that by sort of, oh, let's go to a different color. Let's go green. Drawing in a vertical line, and that's going to be a particular x value. Let's say that's x equals 1.5. Of course, I had to split it right down the middle. And you can tell that the y value on the exponential is much lower than the y value on the linear, right? But let's see what happens in letter B. All right, so we're going to move the calculator over that graph in letter A now. Okay, so now what we're going to do is we're just simply going to change the window. So I'm going to hit the window. All right, I'm going to now 0. Still x min, but now change my x max to 6. Okay, now we'll keep y min at 0, and we'll go down to y max 150. All right, now let's do the big reveal. Let's go up to graph. All right, give it a little bit, takes a little bit of time. While it's doing that, I'm going to go back and switch my color back to blue. I like these graphs. I think they look really, really neat. But look at what happened. Look at what happened. Here's my linear now, right? And here comes my exponential. And it just skyrockets past it, right? There's some point where that exponential catches up to that linear. So I think that we've got the equations down, but uh-oh. Almost ran out of room there. Go back to blue. Have to do what the problem says, label them with their equations. Let's label them with their equations. And there they are, right? So the exponential, which really lagged in exercise A, now catches up in exercise B. And that's the final question of this lesson. Take a look at C. Although the line appears to rise more quickly than the exponential at first, the exponential eventually catches up to the linear. Why will an increasing exponential function always catch up with an increasing linear function? So I want you to think about the last exercise. I want you to think about what you saw in this exercise. And then I want you to pause the video, and I want you to try to give a good, well-reasoned argument for that question. This is the one thing I really don't like about these screencasts, is that right now the teacher inside of me wants to know your answers. I want to know your answers, and I don't know what they are. I'd be very curious if any students do watch this video and they want to make some kind of YouTube comment on what their answer would be, or hey, any teachers too. You know, what would your answer to this question be? Now, my answer is pretty simple, right? An increasing, again, sorry if I leaned in a little bit too far, an increasing exponential has a slope that is also increasing. So eventually, right, let me write that down. So eventually, that almost got in there, that U. So eventually, its slope is greater than the linear's. Now, I'm not sure that actually gets the job done. And in effect, we may actually need something from geometry here. So I think this is kind of cool, right? What do you know about slopes of lines? You know, if the slope of lines are equal, those lines are parallel, right? Same slope, they're parallel. They'll never touch each other. But as soon as the slope of one line gets greater than another line, it will eventually hit it, right? And that's the real key here. Eventually, that slope of that exponential will get larger than the slope of the linear, and it will catch up to it. In fact, what's really remarkable about exponentials is they're basically the fastest function out there. And all right, so that's not true for the pure math people, but they're pretty darn fast. They catch up to anything. If you had something like an x to the 10th, they'd outpace that eventually. An x to the 10th, nothing grows fast. Anyway, I'm going to scrub out the text, so copy down anything you need to, and then we're going to get rid of it. All right, it's gone. So let's finish up. All right, so that was our lesson on linear versus exponential, and I hope what it did is it gave you the similarities, which were they both have starting values, and they both are really repeated applications, linear of addition, exponential of multiplication. But they share a lot of similarities, and of course, there are a lot of differences, the biggest one being that a linear function has a constant average rate of change, and an exponential has a changing rate of change, always increasing if it's an increasing exponential, and always decreasing if it's a decreasing exponential. Anyhow, thank you for joining me for another eMathInstruction Common Core Algebra 1 lesson. I'm Kirk Weiler, and until next time, keep thinking and keep solving problems.